In this video, one will be able to understand the theoretical calculations and conduction of the experiment verification of maximum power transfer theorem. So I am Mohan BS, working as assistant professor in Department of EEE, SJBIT. So here is to determine the value of RL, and also we will verify the same over hardware as well as over software, and plot the graph for Pmax versus RL. So basic theory, the maximum power transfer theorem states that to obtain maximum power from a source to the load, there is maximum power delivered to the load only when your RL is equal to RTH, that is the internal resistance of your entire circuit apart seeing from the load side. This principle applies in electrical circuits and is particularly relevant in the context of DC and AC, but let us restrict our discussions under DC, because under AC we have impedance, which is which involves some other definitions and formulas. So determine Thevenin equivalent to find VTH, open circuit voltage across the load, and then RTH, there is a total equivalent impedance or resistance absorbed across the load. The circuit is seen from the load side. So for maximum, to transfer the maximum power from the source to the load, as discussed, RL, the value of RL should be equal to RTH. Applications: audio system, radio frequency, communication network, battery charging, sensors application, and power amplifiers are some of the applications of maximum power transfer theorem. So let's see how do we solve theoretically for VTH, RTH, and then over PSpice. So calculations for VTH. So the first thing is remove the load, the value that we must find. So remove the load resistance and assume the ends as A and B. Now to find voltage, when you see it through this window through AB, voltage across which all elements is VTH. We can observe voltage across 330 and 470 will give us voltage of across A and B, right? But if you observe, there's no current flow through 330 because the circuit is open, right? Thus we can reduce the circuit further by removing that 330 ohms. So let us further reduce this to understand a simple concept. We'll be applying some simple concept to find voltage across A and B. The same circuit can be rewritten in this syntax. So this circuit we have removed 330. I hope you understood why, because there's no flow of current. Thus we have removed, as there's no current, voltage of across 330 would be 0. Now do you think the redrawn circuit here, over here in this area, you think the circuit is correct, or you think there's something wrong? So please take some time, pause the video, analyze that is there something wrong in the circuit, and unpause to know your answer. I hope you have got it right. The point A was connected between 470 ohms. So now we have to apply voltage divider. Let us apply voltage divider to find. So voltage divider says I want to find VTH, which is nothing but VAB, which is nothing but main voltage, that is 20, into same resistance, that is 470, divided by the sum of the resistance 1K plus 470. So this 1K is this resistance that we are taken into consideration, not this, as voltage across this 1K is nothing but 20 volts as they appear in parallel. The same 20 volts also appears across these two. Thus for this loop, when we apply voltage divider, we are getting the answer as 6.394 volts. So this is VTH, or open circuit voltage across the load element, that is VTH or VAB. Now as we solve for VTH, let us find out for RTH. So let's analyze. So VTH we have done. So to find RTH, we say we have to make the effect of all voltages and currents 0. So making the effect of all voltages to 0 and currents also to 0. So voltage zeros are under short circuit, current zeros are under open circuit conditions. So as we see voltage, one has to short circuit this to see the effect of only resistances. Now if you observe, this 1 kilo ohm and this wire having 0 ohms are being short circuited, or they are being parallel. Thus its equivalent resistance is being 0, that is 1K into 0 divided by 1k plus 0, its effect is 0 ohms. Thus the circuit is still further reduced as seen from the load. Now, so here it is clear that 1k and 470 are in parallel. 1 kilo ohm is parallel to 470 ohm, and this entire resistance are parallel with 330 ohm. Thus we can say RTH or R equivalent is simply 649.728 ohms. So 649.728 ohms is the RTH. Now with the help of Thevenin equivalent circuit, let us find the maximum power that has been transferred to the load. So Thevenin equivalent circuit, we have voltage source, open circuit voltage in series with the open circuit resistance across the load are connected in series. This represents as similar to your practical voltage source. Now connecting the load resistance across AB, which we had removed, and the maximum power occurs only when RL is equal to RTH. Now Pmax is given by the formula VTH squared divided by 4 into RL. Substitute the value of VTH 6.394 into 4 into the value of RL, and or RTH both are same here. We get the power as 15.731 milliwatts. So this is by formula. You can also find out power, as we know it is I square into RL. Find the current and then multiply that by RL, or find the voltage across the load, its square divided by RL will also give us the power. So using any one method, either by Pmax, either by I square into RL or V square by RL, any one of these three methods one can find the maximum power. So let's see this table column which is there in your lab manual, and what are these actually. So VL formula to find out power, to find out the voltage, in order to find out the Pmax. So VTH main voltage into same resistance RL divided by sum of the resistances 649.728 into RL will give us this voltage drop. Assume that we have a voltmeter, right? So I'm finding voltage drop here. Then how do we find the power? How do we will be concentrating on these two. So let us first find out the voltage drop across the resistances, that is RL, and then its power practically, right? So here the fourth row is given only when RL is equal to RTH, what are its voltage and power, and then the first three are the values of resistances below RTH, and the rest three are assumed above RTH, right? So now, so for this column it is VTH, that is 6.394 into RL, which is 10 divided by 649.728 into RL, that is 10. So this gives us then voltage of 96.63 millivolt. Similarly for 100 it is 6.394 into RL, which is 100 divided by 649.728 plus 100. So this will give us around 853.184 millivolts. Okay, so these are the voltages with respect to 10 volts and 100. And then now when we vary the RL from 280 to 280, these are the values of voltage drop across the load resistance. So if I take a voltmeter and find the voltage with this polarity, I get these voltage drops. Now let us find its power. Now let's do it for the first here, this column here. So power is VL max, that is 96.963 milli, V square divided by RL, that is 10, right? So that will actually give us 940 microwatts. I repeat, it is 940 microwatts. Similarly, let us do for the second row, that is 853.184 milli, V square, that is VL square divided by RL, which is nothing but 100, will give us 7.279 milliwatts. So similarly, when we do for the other rows for 280 for when RL is equal to RTH for 1000, 180 and 280. You can see we can plot a graph, or you can observe that the values are actually rising. It reaches maximum and then falls down, right? So this is x-axis, you'll have RL. As resistance changes, you can see y-axis, that's your power, right? And this is your Pmax. And at this point, only when RL is equal to RTH, you can see maximum power. Here we have 10, we have 100, we have 280, for example, what we have considered, and over this area we have 1000, 1800 and then 2800. Only at this point, when RL is equal to RTH, you get maximum power. So in this way, one can plot a graph to observe the variation of RL with respect to the given voltage and find out its power also. One can also solve VTH by mesh analysis, assuming this as I1 and I2. For mesh 1, you'll be writing this as 20 plus 1k I1 is equal to 0, or you can solve that I1 is equal to minus 20 milliamps. And similarly, for mesh 2, one will write this as 1k I2 plus 470 I2 minus 20 equals to 0, right? Or after solving this, you'll get I2 as 13.605 milliamps. And then what is VAB, right? Or what is VTH? It is simply I into R, where I is just I2, right? And by substituting the value of I2 and 470, you'll get the answer as 6.394 volts. You can also solve this by node voltage analysis. So considering the upper one as the positive node and the bottom one as a reference, thus the circuit is reduced. We'll assume the top one as VA. You can see the reduced circuit at the bottom. So now this is positive, this is assumed ground, so we can simply say that VA is equal to 20 volts, as there is no resistance here or here, right? So now as we found VA, we must find the voltage across this, right? How do we find voltage? So we know by Ohm's law V is equal to I into R, where the value of R is 470. And now how do I find this current going down? Now current going down by node is given as VA whole divided by 1K plus 470. Substitute this value of I, we get V is equal to VA divided by 1K plus 470 into 470. So if you see, this equation is nothing but your voltage divider. This is the if you refer, this is the voltage divider what we have applied, but the method is actually by node voltage analysis. So after solving this, you substitute 20 here, you get the same answer, that is 6.394 volts by node voltage analysis. So any theorems, they don't ask you to particularly solve a mesh, nodal or source transformation. Whichever is feasible, whichever you can do it quickly, you can use that method. So let's see simulation over PSpice and verify our theoretical calculations. So first let us get all the parts. That is resistance, we need 3, 1, 2, 3, 4. Let us place them accordingly. And the part name for DC is VDC. Place your voltage source as it is, right? So now let us zoom in and let us connect the keypad shortcut is Control W. Let us first connect all these according to the given circuit diagram. Now let us value them. This is 1K as it is. This is 20 volts. This is 470. This is 330. Okay. Now, as we have valued them, now we have to find the voltage between these two. Then click on File, Save As, save your file by giving appropriate name. appropriate names, and then go to markers, keep voltage differential plus and minus, and the output that you want to see in DC, so click on or enable transient. So print step for DC circuit, it's not a matter because it does not changes with respect to time. If it is 1 volt, it is 1 volt throughout. It's not changing with respect to time. Okay, then save, simulate. By this you'll get an error stating that float R3 pin is, floating pin R3's other end is not connected. So this is a circuit that we had actually done in theoretical, but over in PSpice, no, we cannot simulate this circuit. We cannot leave open circuit. Neither this cannot be connected to ground, because this, if I connect this to ground, there is some amount of current flowing. So we have to nullify this. So let us not delete this. So what we can do is we have to create an open circuit. So how that can be achieved is by creating R5 with a large value. Let us say we put 6 or 7 zeros. So this, by this value R5, we are just simulating it with a open circuit, right? So we have enabled transients, save a file, and now simulate to check your output voltage. So now we have got an old voltage, something above 6. So how do we see this? Hit on toggle cursor, the probe cursor appears here, you can see, and the voltage you can see at any given time. At any given time it is same. So that's why we have not bothered in DC circuits or in this experiment with respect to time here. It is 6.3946 is what we have got our output. Now, as we have done with VTH, let us now solve for RTH. So for RTH, to do that, what you can do is, let us label this as VTH, right? Now let us delete the voltage probes. Let us copy paste the entire circuit. So remember, we have two, this is VTH, and over here we have RTH. So let us rename it. Now RTH, what do we do here is, let us remove this, as we do not have separate ohmic meter in PSpice. So what we are doing here is, let us use application of Ohm's law. Let us connect an 1 volt DC supply, beg your pardon, let us take 1 volt DC supply, 1 amp DC supply, connect it across the load, revalue this to 1 ampere. So as we know, by Ohm's law, that R is equal to V by I, or R equivalent is equal to total voltage by total current. So here we are taking the total current as 1 ampere. So what we find is, we'll find what is the voltage across A and B, right? So that voltage will substitute this place, and its ratio will give us what is R equivalent. So go to markers, we'll find what is the voltage across these two ends, simulate. So toggle cursor, so you can see the value as 656.12. That's because of the internal resistance of this voltage source. So as we're finding resistance, as discussed in the calculations, one has to short circuit the voltage. Let us simulate again. Now let us check. Yes, the value of R equivalent is 649.728, the same that we have got in theoretical calculations. So this is how we have to simulate for VTH and RTH over PSpice. Now, as we've done with VTH and RTH, let us plot for Pmax. So let us delete the probes. Let us do that in the same file. Let us zoom out. So for that we need VTH. Let us take 1 VDC. We need 2 resistances. We need a ground. This EG and D is the part name for ground. So let us zoom in this area. Let us connect wires. So this is Thevenin equivalent circuit. VTH was 6.394 volts and RTH was 649.728. Let us rename this as RTH. And now to simulate for the graph, let us the value of this resistance, that is RL, as in flower bracket as capital R and capital L, and close of our flower brackets. We take one more parameter called param, or it's known as parameter. So param or parameters is the part name for that. So double click on this, name what we have given, RL, and the value. Let us, in theoretical we have given up to 2.8K. Let us give as it is. Done with these settings. Now go to setup analysis, go to DC sweep, not transient, to find the graph. Click on DC sweep. Now it's a global parameter as it's outside the circuit. Name given is RL. Start value, you cannot start from 0. You can give any value, any numerical value greater than 0. End value 2800 is what we have given. Let us say an increment by 20 ohms each. Now, so let us find the voltage across RL and current through RL. Let us simulate. This is the graph that we get. What you can do is copy paste this value of current. So as we know, the formula for power is V into I square into RL, or V square by RL. So V into I will also give us the power. So in this way you can see the plot. You can see here it is 2.8K and you can see it is 16 milliwatts. So this is the graph that we had discussed earlier. Click on toggle cursor and this is your cursor peak. So it is on 15.73 milliwatts. That's the exact value that we had simulated, right? So do not worry about this value 641, because our value was 649. So there's a small variation, but still this is the maximum power that we have got. That is 15.73 milliwatts. So this is how we have to verify for VTH, RTH and maximum power over for Pmax for maximum power transfer theorem. So remember, the circuit must be inspected by lab instructor or faculty before you energize. Thank you for watching the video. Please do subscribe our YouTube channel to enhance your knowledge further.